Hi, everyone. Thank you for joining this technical day. So I'm really happy to organize that this year, like last year, and I see a lot of our users here, so welcome. So now we have done a small introduction to that talk. I will just go back to the new features before the demonstration. So we're going to present you our new features in 2 workflows this year. So slightly different from usually. And this presentation, this workflow will be based on a specific database, a data set that I'm going to present. So if you are able to see my screen, so yes, we're going to work on the Slackner field, which is located in the central part of the North Sea. And since 1996, the Slackner field has been used as a facility for carbon capture and storage. And what is incredible is that that field is the world's first offshore CCS plant. And every year, about 1 million tons of CO2 from natural gas is captured and stored. So it's a really interesting project. In terms of just very briefly the geology, the reservoir is the Miocene Utsira formation, and it is composed of interbedded and cemented set package and shales. And the reservoir is covered by 100 to 50 meter Pliocene seal. So that's what this is the data set we're going to look at, and especially the Utsira Sen, we will try to map precisely that area. So we will see 2 workflows today: how to enhance your geobody volumetrics using PaleoScan Avio post-stack attributes, and how to improve your reservoir characterization using PaleoScan extending elastic impedance. Okay, so the objective of the first one will be to be able to extract a geobody representing the zone of injection of gas. The first step of the workflow is typical workflow in PaleoScan. So we start by the conditioning of the data, which is a step to perform signal enhancement, noise reduction. And this will be very useful for facilitating the model grid auto tracking, as well as improving the behavior of Avio and inversion. So in that case, we will apply the structure-oriented smooth that provides a smoothing steered to the depth of the seismic amplitude. And then we will apply a new attribute that is available in our data conditioning toolbox, which is the spectral balancing. So that attribute aims at enhancing the vertical resolution of the data by boosting the high frequency without overlying boosting the noise. Once this is done, we can move on to the next step, which is the interpretation. So if you're familiar with PaleoScan, you should know the workflow where we create a regular grid of patches, which are sort of micro-horizon. Then these patches are automatically connected based on the similarity of the amplitude and relative distance. And what is the key in PaleoScan is to perform the refinement. So this is a semi-automatic method. The personal and the geologist and geophysicist input is really important. You should disconnect, connect patches based on your understanding of that area. And once this is done, we will be able to generate the relative geological time model, which is just a vertical interpretation of your model grid. You have access to a blending viewer, and Sven will present you to that in a minute, where you can look at your RGT model compared to the seismic and QC it. Once this is done, you can extract a set of isotime surface, and this set of surface will be what we name the horizon stack in PaleoScan. We will map several attributes, so the seismic, but also a new attribute that is now available in PaleoScan, which is the average energy. So it measures the reflectivity in a specific time window. This is a really great attribute because it enhances the lateral variation within seismic events, among others. And therefore, it's really useful for seismic object detection, amplitude anomaly, chimney detection. So we will use it today. And now, if you want to go a little bit further, we're going to use a new tool available now in PaleoScan, which is our new Avio attributes tool. And it will allow you to compute Avio attributes from post-stack volumes to assist you in identifying the fluid content or lithology information. So there's 2 algorithms available. In our case, you will see we will probably use the first one, the Tour-Dem-Chouet approximation. It just depends on the angle of your post-stack volumes, of your gather volumes. So now we have two kinds of data. The attributes map on the horizon stack. We have our Avio volumes, and we will use these two sets of data to generate and extract geobodies. So we will do the two kinds of extraction, one directly from the horizon stack, and one we will use the cross plots that are available in PaleoScan, and we will cross plot the intercept and the gradient, which is a widely used cross plot in hydrocarbon exploration. Once this is done, we will just compare the two volumes, see which one is the most accurate. Hopefully, the Avio will help us to better characterize our gas injection zone, and we will compare that to the literature volumes. So that's just all with the first workflow. You see there's a number of new functionality this year. I will now move on to the second workflow before letting the control to my colleague that will do the demonstration with PaleoScan. So the second workflow will show how to use the extending elastic impedance. And this is a tool that will give the promise of a fast and objective way to relate seismic inversion results to different reservoir properties, such as the porosity, the fluid content, and the lithology. So it's a very useful tool for exploration, prospect evaluation, and early reservoir characterization. So today what we will do is to compute a quantitative porosity volume based on our well logs and angle stack volumes. First step, so you will be able to open our a new window in PaleoScan. You can select wells. From your VPVS and density log, you can compute a number of composite log in PaleoScan. And if you want, you can choose one of these composite log to map them into a volume properties. Or you can select another reference log that could be the porosity in our case. Once this is done, we will need to find the correct key angle projection used for relating the extending elastic impedance to that porosity. And for that, we have a very useful tool, which is the angle with best correlation, where we're going to test a number of key angle to find the maximum of correlation between the extending elastic impedance log with the porosity. You can, for sure, this is in case of one well, but the more well you have, the best it is, and the more accurate will be your volume. So don't hesitate to use more wells, and we have a tool for that to find the highest mean correlation in that case. So at that step, we have the Eei log at a specific key. And now we will need to compute the associated reflective volumes. So we have also implemented a new window for that, where you use your near mid-far volumes, or if you already have your intercept and gradient, that's great, so you can directly use them. But our aim is to get at the end the reflective volume for that match that specific angle key we've defined at the first step. Once this is done, we have everything we need for the inversion. As you may know, inversion, in our case, we will, because we want some absolute values at the end, we will build an a priori model using our property modeling tool. So for that, you can go through the workflow we have just seen before, creating the model grid, interpret key fasces interface, propagate the EEI through the property modeling, and do a low-pass filter. And we have an a priori model just here. Once this is done, we can perform the deterministic inversion. So we have a new algorithm in PaleoScan this year, which is the least squares inversion. So please try to use it. That's a really good improvement. And at the end, from the inversion, we get the inverted volume of extending elastic impedance value, which is there. And to get the porosity volumes, it's a simple linear regression that is applied, and it corresponds to the correlation between the Eei logs and the porosity that we have seen at the beginning of the workflow. And what it is great is that at the end, we have a volume of values similar to the porosity logs, but with a resolution close to an inversion results. So we have that volume. If you remember last year, and we have presented to you the geocellular grid, actually 2 years ago, I assume. So we will now create a geocellular grid for our reservoir and map that new properties inside to get some volumetrics and see where had the highest porosity area. And we have a new export format, which is the RSQML format, so you will be able to export that grid directly from PaleoScan. So that's it for the workflow. I will now let my colleague present you this workflow in real life in PaleoScan. Enjoy.
Thank you very much, Marion, for these new features. Yeah, I'll give the word to Sven now.
Hello, everyone. So my name is Sven, and I'm glad to spend a bit of time with you to have a quick presentation of a demonstration workflow in PaleoScan 2021. So right now I'm going to share some the application with you. And if you can all see my screen, so to catch up with the location context that Marion told you about. So today we're going to see a workflow that covers the Sleipner field. So for the geographic location, you can recognize on this map in the interface of PaleoScan, the Scotland to the left, so to the west of this map, and the coast of Norway to the east. And what you can see in color in the middle is the isopack of the Utsira Formation, which contains the sands of the field at the Sleipner field. And now, if you're looking at the southern part of this isopack, by the way, whose reddest color are representative of about a pile of sediment about 350 meters of deposit, then you can see on the southern deposit well there where the Sleipner field lies. So done with this, and to just allow you to have a look at the evolution of the gas injection through the Sleipner field through time, I want to show you this session here where you can see on the left seismic as recorded in '94 before the beginning of the injection, and you've got an evolution through time in these 5 different slices. And the final results of the injection in 2010 after an injection of about 12 million tons of CO2 in there. So through time, you clearly see that we can monitor these CO2 injection and the influence of the seismic, because you've got some growing reflectors, both in terms of amplitude and in lateral extent. Okay, so now we want to start from the initial seismic in '94 to create, to interpret the geometry and to create a geomodel, so that we can later on create a horizon stack out of the geomodel and then be able to map the anomaly induced by the CO2 injection and characterize this anomaly in terms of volumetrics. So the first issue is that, that we're having now when we're starting with this seismic is that in the Utsira Formation, that is about in the middle of this seismic, so between the 2 bright reflectors that I'm pointing here, so the one at the top here, the cap rock, and the one at the bottom here. If I'm zooming closer to the seismic, you'll get aware that the seismic resolution is quite poor. Well, we've got a lot of noise here, and the reflectors are not so continuous, and on top of this, they are not quite strength in terms of amplitude. They're not quite strong in terms of amplitude. So if we want to improve later on the model grid interpretation in PaleoScan and then to be able to create an accurate geomodel, we're going to need to perform a bit of conditioning on this to improve these next steps. Okay, so I would like to show you 2 steps of conditioning, and I'm going to spend more time on the second step from the seismic. What I'm going to do in this seismic is that I'm going to apply a structure-oriented smooth so that I can increase the lateral continuity of the reflectors. And on top of this, I'm going to apply a spectral balancing on the seismic. Okay, so the spectral balancing is a new feature from PaleoScan 2021. So let's get to it. So again, I'm going to skip the stage of the structure-oriented smooth. You're going to see the result of it in a few minutes, in a few seconds. But what I would like to show you is the interface for the spectral balancing. So you can find the spectral balancing in the attributes list that we have in PaleoScan. Here is the interface that we have. And as I told you, I'm going to start from a seismic from '94, where I've already applied some structure-oriented smooth. So this is why you see these SOS in the naming. So see, when I've applied the structure-oriented smooth in the Utsira Formation, especially above and for the bottom reflector, we've increased the continuity of the reflector. So this is going to help the interpretation in the grid. But you notice that the amplitude of the reflectors is still quite dim. Okay, so if we want to improve this, I can just put my cross navigation seat somewhere in the location where I want to get a preview. and apply a spectral balancing. So here with the default parameters, this is the preview I have in my square box here. So you can see that already the amplitude of the reflectors are being enhanced. So that's good news. And you can also control the improvement of your balancing through the amplitude spectra. Okay, the blue curve being the initial curve, and the red curve being the one that is balanced according to your parameters. So to save a bit of time here, I'm going to directly show you the results of this computation here. Then you're going to recognize the three steps, the three different steps of the conditioning, and see step by step the improvement that we're doing. So here to the left, you recognize the seismic that we had from the beginning, and then to the center, you've got the structure and its move, and to the right, sorry, you've got the result of the structure and its move plus the spectral balancing. So this time, we've got a compilation of several steps of conditioning where we've increased the continuity of the reflectors, and there you can see that the reflectors inside the Haute-Sierra formation are a bit more pronounced. Okay, they're a bit strengthened in terms of amplitude. So it's going to help us a lot in the interpretation of the model grid, okay, which is the framework for the seismic interpretation. So talking about the grid, so let's go to the model grid right now. So I'm going to open a model grid so that you can actually visualize the impacts of our conditioning on the grid. All right, so you've got, you've got the model grid here on the left, and you've got the time map viewer associated to the grid on the right. So you've noticed on this interpretation that I've already interpreted the top of the cap rock here, and another reflector which is actually below the Haute-Sierra formation. But now if I'm taking, for example, the base of the Haute-Sierra formation, you're going to notice that thanks to the continuity that has been improved, okay, then the connection of the reflector is going to be enhanced. And even if I'm looking inside the formation itself, so I'm just going to take one random reflector here, you're going to notice that we're going to be a bit quicker in the interpretation here, as if if we had not conditioned those seismic. So okay, so little by little, I'm going to connect these reflectors, and with this, I'm going to refine the grid to allow the creation for a future geomodel. So here we're previewing the model, okay, and you're noticing that this way we're filling up the model and getting something accurate in the end, okay. So I'm going to show you the results of the final model. So here, that was just a preview that we had. So what if we want to QC the actual model that was produced out of this grid? So we're going to use, for example, a blending viewer. I'm going to compare the initial seismic that I've played with, so with the total conditioning, structure and its move, plus spectral balancing, and blend it with the model. And here, if I'm zooming a bit so that you can see the detail and playing with the blender, you're going to see that inside the formation, okay, you're going to have some accurate representation of the geometry of the seismic in the geomodel. So based on this, we're going to be able to generate some horizon stacks to map the anomaly of amplitude, such as we observe it in 2010. So I'm going to close this interface and pretend I'm going to create a horizon stack based on the geometry of this model here. So if you want to create a horizon stack, you go into the dedicated toolbar for the horizon stack. You're taking geomodel of reference. Okay, and this time you can pick up a seismic of reference. So you can pick up, for example, the one that includes the anomaly induced by the gas injection. Okay, and then I'm going to be able to fix a top and bottom limits, so that will correspond to the top and bottom of the formation, of the Haute-Sierra formation, for example. So that would be this interval. And then I'm going to input a certain density of horizons in there. So by default, it's 100, but you could increase this value up to several thousands. Okay, so that would be a bit useless in this case. And then next stage, you're going to map any information you want on top of these horizons in this stack. So to skip or to jump forward a bit quicker in the workflow here, I'm going to show you the results of the mapping of different informations, different attributes on this horizon stack, on which we can observe the impact of the gas injection. So here to the left, you have the vertical section of the seismic in 2010. So you can see again the anomaly of the injection. And when I'm scrolling, you're going to be able to see on the viewers to the right, the anomaly. So just to explain what you've got in front of your eyes. So to the top, you've got a mapping of the seismic, just the seismic information to the left, and of the new attributes from 2021, which is the average energy. So it's mapped from 94, so this is why we can't see anything. And on the bottom, for the same relative attributes mapping, we have the results and the impact of the CO2 injection. So you can see and cross-navigate through there and observe this anomaly. So from there, you could use, for example, the average energy, okay, which is where the CO2 injection anomaly is clearly highlighted. You can use this window to create a geobody and to get a first analytical result about the volumetrics of this anomaly. So if you were willing to do this, because the anomaly is clearly visible on this horizon, you could play with the semi-automatic method of creating a geobody in PaleoScan. So playing with this blue filling tool here, adapting the threshold to comprise whatever amplitude here that would correspond to the anomaly. And again, with the geobody toolbar, which is dedicated for the creation of bodies, you're going to, horizon by horizon, you're going to just select every blue patches that you would like to see in the end part of your future body. So you'll do this for every horizon where you can see the anomaly. Again, because I want to save a bit of time here, I'm just going to show you the result of the geobody creation with this method. So let's go for this. Not going too quick in there, so my body is here. See, it's from horizon stack method. So I'm going to open it into a 3D viewer. So that's my 3D viewer. Okay, and I'm visualizing my geobody. Just for the reference, I'm also going to show you the top of the Utsira formation, which is this horizon here. So what do we observe here? We observe that in general, the trend of this geobody sounds logic. I mean, it has a shape that translates an accumulation of gas going up in the different sands units of the Utsira formation. But you can see that it seems thick, and in particular at the level of the cap rock, so at the top of the Utsira, you can see that this geobody is going above the cap rock, which is not supposed to happen according to the literature. So here, maybe our method is not so accurate. So to compare another method with this one, we're going to try to use the Avio, which is also new in PaleoScan 2021, and see what we can do with an analysis of the Avio and using also the cross plots. So if you want to use the Avio in PaleoScan, you're going to have to go into the volume toolbar, and there's a specific button for this where it's named Avio here. You can click on this, open this interface. All right. In this case, I've got different volumes with variation with offset available. So I'm going to use, of course, the data in 2010. So I'm going to drop the near, the mids, and the fars in there. And I'm going to assign a corresponding angle to each of them. So first one's going to be 11, 22, and 33. Okay, and then from that, I can use two different methods according to the ranges of angles that I have. So either the Schuet term on the or the Penengarder method, with in each case a series of attributes that I can generate. Because here I'm dealing with angles that are lower or close to 30 degrees, it's more adapted to use the Schuet term equation. So I'm going to use this method. And let's say I'm going to create the primary attribute of this method, which are the intercept and the gradient, and let's say another one, which would be the gas indicator, okay? If I wanted to compute these guys, I would have to click on Save here, and the volumes corresponding to these attributes would be created. Again, I've already created them, so I'm going to present you first the gas indicator. So if you want to have a look at this, here is the result of the creation of the gas indicators. I'm just going to remove the geobodies that is intersecting this background. And you can see again that the gas anomaly here, well, the amplitude anomaly that is generated by the gas injection is clearly highlighted, whereas the background noise is kind of reduced compared to a classic seismic. So it's quite interesting to use these attributes in this case. But if you want to be a bit smarter, we can either go to an Avio analysis through the crossplot of the gradient versus the intercept. And this is what I propose you to do right now. So on live, we're going to do this. So we need to use a 2-channel blender. And then we're going to use and drop R2 intercept and gradient volume. So from there, we've got the blending of these two information in this blending viewer. We can still play with the slider to play with the blending. But more interestingly, we can open the crossplot section corresponding to this. Okay, update the crossplot to see the data. See the data here. So just as a tip, you can choose only to visualize the density of the crossplot if you're just removing the points. Okay, that's going to look like this. Or conversely, you can only show the data if you're more interested in just visualizing the data. You can also reshape the geometry of this, just in case. Okay, here, for example, I want to see my trend line, which is diagonal, so I'm going to squeeze it a bit. All right, so this is my trend of data corresponding to these gradient versus intercept crossplots. And now what I could do, I could just sample the specific data that I want to analyze from my blending viewer by just brushing a sample of it in here, okay, like this, for example, and choose to show whatever I've sampled on the plot. But in this case, because we're doing an Avio analysis, I've already some classes, some Avio classes that are prepared from before that are corresponding to specific section of this graph. So I'm just going to use them directly to perform an analysis. So in this case, I'm just going to go in my project browser, my database, just have to drop these classes and see how I can, what kind of anomaly I can see through there. All right, so if I'm zooming out a bit again, so you see different classes in here, and as soon as I've plotted my classes on the crossplots, then the result of my class selection appears on the blending viewer with this dynamic mapping, okay? So just to be quick on that, we are in the North Sea, so by convention, the polarity is reverted. So everything that is going to be above this trend line, in this case of these Avio analysis, correspond to classes relative to base reservoir. And everything that is to the bottom correspond to top reservoir classes. So in here, I know we're dealing with gas anomalies. So, and I also know that the reservoir is not necessarily saturated in every sand unit of the reservoir, so I'm rather focused on the lower part of my trend line. And you can see that basically, if I'm just removing the show plot here, that's I've got plenty of my data that falls into this yellow class in here, which is the class 4 for the top reservoirs, okay, in this case. And you don't have anything or no much things into the orange quarter down there, which correspond to class 3. No things around the origin of the intercept that correspond to class 2, class 2P, and no much information into class 1 in blue. Okay, so it seems quite consistent with this gas anomaly down there. So if I want to output a geobody that would correspond to just this class here in yellow, that correspond to the top reservoir, ignoring everything that is on the base, so on the upper side of the trend, I would just have to preserve in my list just whatever attribute that concern the class 4 on the top of my reservoir. Okay, so I'm going to delete some classes like this. And just to save a bit of time, I'm going to directly go to the geobody creation. So little by little, you see that I'm only going to preserve the yellow class, the class 4 for the top. Going to output creation. And here I would have to create on create geobodies. And eventually, all the classes that you can currently visualize in the blending would be created. So I'm asking you to trust me now, and I'm going to show you the result just for the class 4 in yellow, corresponding to the top of the reservoir. So a bit of loading so that we can see the results in the 3D viewer. Here we go. So if I'm zooming in, again, you can recognize in brown the cap rock. And in the kind of a grayish layer, you've got the base of the Utsira formation. And this time, if we're looking at the geobody that was created from this crossplot analysis from the Avio, then you can see that we recognize some much more accurate definition of the body with distinct layers that are induced by the compartmentalization, the vertical compartmentalization of the sand units in the Utsira formation. And this is consistent with the literature. And you see that the topmost of the layers is beneath the cap rock, so it sounds consistent. And if you want to have a rough volumetric analysis of these bodies, you can return to the geobody toolbar. And for example, here, if I'm comparing the geobodies that I've created with the two methods, okay, you've got the first one from the horizon stack mapping from the average energy, and the second one, or no, it's the top one now, from the Avio analysis. Then I can see that I'm much more accurate in terms of volumetrics for the geobody that have been created with the Avio method. Of course, it's these values here are taking into account in comparison with the literature, taking into account the porosity, the saturation, and like parameters like this. Now, if you want to be even more precise, this is where you could go through the inversion workflow. But for this, I'm going to leave the floor to Jake. And yeah, so thanks for this for your attention on this part.
Thank you very much, Sven. Jake is coming. Yeah, Jake, it's your. Oh, I think we lost Jake. Okay, Jake, are you able to come back? Yeah,
yes.
Very good. Thanks.
Hello, everyone. Well, thanks for the introduction. I will be going through the Eei workflow as described earlier. So hopefully you guys can see my screen now. All right, so what we're going to do today is just go over the brand new Eei workflow that we've developed for the 2021 release of PaleoScan. We're going to start off here. The objective of this workflow is to map a reservoir property into a pre-existing geocellular grid, and we're going to do this using this new Eei workflow we talked about. So we find the new Eei workflow in our reservoir module at the very end. You see the Eei button here. If we click on that, the extended elastic impedance workflow will open. And we're going to work from left to right across here. We're going to start with the Eei Logs Creation. So we need to bring some well log information into this window, and we can do that by either clicking on this plus sign here, or we can simply drag and drop the well or wells that we want to use for this workflow. Now the software is going to do a pretty good job of recognizing the logs associated that we need to create our composite logs. But in the event that you've got a specific nomenclature, maybe that's a little different than what the software will recognize, you can always select the appropriate logs. And once the software reads those, you see how we've updated, and it automatically is going to go through and create a number of composite logs. And so you'll see from left to right, we've got our P sonic, our S sonic, our density, and then the rest are all the composite logs that the software has automatically created. So we've got acoustic impedance, extended elastic impedance, VPVS ratio, bulk modulus, Poisson's, Lemay's, just a host of all of these well logs that the software will automatically create for us. Now, if we wanted to, we could, like Marion said, output any of these logs by turning on any of these output options. But today, what we're going to do is we're going to try and map an extended elastic impedance to our porosity. And so what we need to do is define a log, and in this case it's going to be porosity, that's going to allow us to match the best chi angle to our elastic impedance. So what we'll do is we'll select the reference log of porosity in this case. And now what we'll do is click on our correlation viewer. And when we see the correlation between our input logs and our reference logs, so porosity. And so what we do is we're going to click on the angle with the best correlation button. And you'll see the software automatically calculates the best correlation between these logs, and we find that the best correlation that we can get here is a 0.85, which is not bad. Anything about 0.8 is pretty good. And we find that chi angle is at -5 degrees. So we want to save this Eei log to the well. So we'll come down here and I'll turn on the extended elastic impedance log option and click save, and that's going to save this log to the well or wells that we have used for the input. Now we'll use that later to propagate into our geo model to build our impedance volume, but before we do that, we're going to create our reflectivity volume. So moving left to right here, we're going to click on the second button here. This is the reflectivity volume creation button. We have two methods available to us. We can use our angle stacks. So if we have our near, mid, and fars, and we know the angles associated with all of those volumes, we can use those as an input here. But Sven was gracious enough to create the intercept and gradient volumes, so I figured, why don't we use those? So I'll change over to the intercept and gradient. And we'll just bring those volumes in here. Now, like any input window in PaleoScan, there's a number of ways to get data into those, and I like to just do the double-click method, where if you double-click where it says drop here, you have a list of all the available inputs. And so for this first input, I'll select intercept. For the second input, I'll select gradient. And now I'll tell the software to create the output volume of our reflectivity based on the extended elastic impedance, and I'll have to make sure that this matches the best angle that we found in the last step. We'll click save, and what we'll have at the end of this process is a reflectivity volume that we'll then use at the end of this workflow for our inversion. Before we do that, and I'm just gonna cancel because I've already done that. What we have to do now is come to our Wells property modeling icon, because what we need to do now is create an impedance volume. So I'll come to my Wells property modeling icon, and now what we'll do is we're going to use that well log that we just created. So I'll select the appropriate well log here. And now another neat option that PaleoScan has is, you guys maybe notice these little magnifying glasses. If you want to use the magnifying glass to figure out which data is available for input, you can always click on the magnifying glass, and you'll see it creates a custom filter off in your project browser showing you only the types of input that you can use. So I'm going to use that well that we started off with and drop this into the input window. And now we're going to choose a model that allows us to propagate that well information into our impedance volume. So I'll double click here, and I have a pre-existing geomodel already created. So I'll select that geomodel and click next. If I expand this window, you'll see now we have either a horizon or a 2D line option. I think for our purposes here, this presentation, the 2D line option is more telling. So I've got a 2D show line. So now we're seeing just a 2D show line, and in the background, of course, is this geomodel that we've created. So the object here is to then create an upper and lower boundary, and so I think we're going to pick somewhere right about here, and then I'll pick the lower boundary right about here. And this is just giving the software the upper and lower boundaries to create this impedance volume. Now we've got a number of different methods to do this. I'll come down, and if I click on interpolation, we've got inverse distance, kriging, and also the co-kriging. Because we're only using one well for this example, I'll just stick with inverse distance. And if I click on the preview button, you'll see that the software is going to go through and quickly build a preview. And this is a 2D preview of the eventual impedance volume that we're going to create when we run this process. And so if we're happy with the appearance at this point, we can click Run. And the software will then go through and create the 3D impedance volume. Now I've already done that. I'll go ahead and open that volume. So this is the result of that last process. And so the cool part about PaleoScan now is what we can do is, I want everyone to direct their attention to our properties pane. And this is similar for any volume that you have. We have a whole suite of on-the-fly attributes, and it lends itself really nicely to help us create our a priori model. So we're going to use this impedance volume to create our a priori model, or our low frequency model, to use for our deterministic inversion. So if I come to the attribute row here, I click on the options here, you'll see here's our whole list of all of the on-the-fly attributes that we can choose to apply to this volume. I'm going to come down to our low-pass option here. Our low-pass option has a number of filter types to choose to select from. Butterworth, Hahn, Hamming, Bartlett, and cosine. And I'm going to use a Hahn pass filter for this one. And I know that a high pass of 10 hertz and a high cut of 15 is going to give us a good a priori model. So now that I've created that low pass filter, what I want to do next is now save that. So I'll come up to my icon in this window, and I click on that once. I'll come down the row and I'll say save as. I'll give this a name and click OK. Now I've already done that, of course, for the purposes of this demonstration. we've already done that. And so now that I have my low pass model, the next thing I want to do is to use the reflectivity volume that we created initially and that low pass volume to perform our deterministic inversion. So again, I'll double click here and I'll select the reflectivity volume. Now we've got, as Marianne mentioned, we have two options. The new option is this least squares method. So I'm going to use that least squares method today. For my impedance in my a priori model, I'll use the low pass model that I just created. And I know that my deviation needs to be a little bit higher than 50, so I like to put it around 80%, just to be a little more dramatic on the output. And of course, we have to select a wavelet to use for our inversion process. I'll select my statistical wavelet. And now the next step here is going to be to click on the preview button. Now, I know this is going to take a minute, so I've already got a window open that's already run the preview. But the idea here is that we want to use the preview to make sure that it's as like a QC step, right? So the idea is before we go forward and run this process, we want to use this preview to determine whether or not the volumes that we've created and the parameters that we're using to make to perform this inversion are going to give us an output that we feel comfortable with. So the idea, like I said, the idea would be to click on preview, and I've done that already in this window. So if we have a look at this, you'll notice just like we saw with Sven's presentation, we've got this alpha blender or this transparency blender that we can use to go back and forth between our input volumes. And so I've run this preview already, and right now we're looking at our impedance volume. And if I wanted to, I can scroll all the way down to see what our impedance volume looks like. And if I go all the way up, now I'm looking at my reflectivity volume. But the idea here is to go back and forth and just look at these two volumes and give us a good sense on whether or not we're happy with the results. Now we can also look at the synthetic that's created by the same process in the same fashion. And it looks like the synthetic is closely matching the reflectivity volume, so I'm happy with that. And then lastly, there's also the residual option. And so if we look at the residual, we do see a bit of a residual signal where we have the anomaly, which is expected. There's very little well control here and here, but otherwise around the outside of that anomaly, we see very little residual. So that's telling me that at this point, we've got a pretty good set of parameters here to move forward with this inversion. So at this point, I can say, let's go ahead and save this. And it's actually quite nice. This is something new that we've included in the 2021 version, is the ability to not only save the impedance volume, but also the synthetic and the residual. And so if we turn all these on, we'll create 3 volumes that we can then use to QC even further, right? Because this first QC look here that we're showing you is really just a 2D preview, right? So because we're creating a 3D volume, we'd like the ability to be able to create these 3 volumes and then pan through and continue to QC to make sure that the parameters work for an entire, for in and out of a 3D realm as opposed to just a 2D preview. So like the other steps, I've already gone ahead and created those 3 volumes. If I open those up, we can quickly tile those together. Let's do that a little better. And using our link function, this is a pretty cool function. If you go to your Windows list, you can link all your windows together really quickly so that anything you do in one window is mirrored in the other windows. So you see I can grab any window and it's reflecting. It's doing the same thing in all the other windows. So here I'm showing my final inversion of my impedance volume. I've got my residual and my synthetic. And so I can use my scroll wheel to scroll through the volume to make sure that we're not seeing any blaring problems, anything jumps out at us. And so far I'm happy with the results. And once I've convinced myself that I'm happy with the inversion, the next step is to now actually go back to the extended elastic impedance workflow and use that inversion to finalize our process here. So I'll click on the reference log to volume creation, which is the final step in our Eei workflow. Of course, we'll use the new least squares inversion for our input volume. And now we need to define the input logs to get that linear regression that Marion mentioned, to map the porosity into this impedance volume. So I'll select the well that we used, the Eei log that we created at the beginning, and also the reference log of porosity. You'll see the software automatically calculates the mean correlation and the linear regression function for this part of the workflow. I'll name it porosity from Eei and click Save. And now I'll open that up. And if I tile all these together, and again, I'll use my link window function to link these all together. You'll see in the upper left-hand corner, I now have my porosity mapped onto my impedance. My synthetic and residual and my initial impedance volume are still open. Well, again, I can scroll through all of these together if I want, just to continue to QC and make sure everything is copacetic. And now there's just 2 steps left. The second to last step is going to be to map that porosity volume into a pre-existing geocellular grid. And then finally, I'll show you guys how to export it using one of the 2 formats that we have. So like I said, the final stage here is to map this porosity volume into our geocellular model. And I'll do that by opening up a geocellular model. The model opens in 3D. I can turn the grid on by selecting the geocellular model, so we see the full grid. And I like to drop the porosity volume in there just to give us a point of reference. So with the geocellular model created, I'll come up to my reservoir module toolbar, and I'll click on and select the data mapping on geocellular grid option. There we go. So I want to map this porosity volume that we've just created into that geocellular grid. I'll give it a name. I'll say go ahead and overwrite that. The software goes through and very quickly writes the porosity volume into the geocellular grid. And what we'll be able to do is, in fact, what I'll do is I'll change the color bar to match the porosity volume. And then we're going to be able to do a couple things to really fine-tune the appearance and the look of this output. And so I'll go ahead and change the color bar to porosity, so now it's matching the porosity volume. And a neat thing we can do if we come back to our properties pane here is, if you notice down in the property range, we can focus in on a very specific range of porosities. And so in our case, we know that the min and max value is being shown, but we're not really interested in the minimum values. We want the max porosity values for this. And so I'll just change this to 0.40 to 0.47. And you'll see now the software has eliminated anything less than 0.40 porosity and included a range of 0.40 to 0.47. So we can get a really good idea on where our highest porosity zones are, and it appears as if the majority of these high porosity zones are in this or within the range of the formation that we expected it to be in. And we can play around with the color bar a little bit to really focus in on even a higher level of detail, to see the even higher level of resolution where the high porosity values are. And once we're happy with this, the last thing that we're going to show you is how to now export this geocellular grid for use in other programs. And so we'll come up here to my export option. I'll click on the geocellular export. Now, traditionally, we did have the Eclipse format was the original format that we had, but like we explained earlier, we've got the 2021 version. We've now included the Rescue ML version. We'll click OK. We got a couple other options to play around with, especially with the output porosity. We can go from discrete to continuous to give us a more blended appearance, and I'm going to allow the options to remain checked on by default. We can set the export location wherever we would like, and then we would click OK. And that's all there is to it. So thank you very much for your attention. Again, if you have any questions or comments, we'd love to hear from you. Either give us a call or send an email. Thanks for your attention, and enjoy the rest of the forum.
And if you have any questions, or if you need a demo, or if you need some help, please feel free to contact us. We have different email address. We have the contact at Eei's or support at Eei's, but we also have different email address for each of our offices in USA, Australia, Brazil, and Malaysia. So please contact us. And just a few words about the upcoming events. So the upcoming Eei's events, we're going to be part of the Geo Days from the 22nd to the 24th of June. And if you want to meet Mathieu and Jean-Philippe in B2B meetings, you need to get there. We also have a workshop with Steve Tobias planned for the 22nd of June. So please, there is still some spots available, I guess. So please get into, you can go to our website and register there. We also have a workshop on the 23rd of June in Argentina, I think, or in Brazil. And we also have a couple of virtual trainings coming up during summer in July and August. We also have one in September and one in October, and a couple of more will come at the end of this year. Exhibitions, as the COVID restrictions ease, we are now able to go to exhibition physically, to attend to exhibitions. So we will be physically there at the SEG in Denver. So please come and see us if you're around. And we also have a booth at the EAGE in Amsterdam in October. So we'll be very delighted to see you physically there as well. And we will also be part of the EAGE conference in Asia Pacific about the Eei methods. But that will be virtually, and also the second workshop in advances in seismic interpretation in Abu Dhabi with the SEG, and that also will be virtually. So thank you very much for attending. Thank you very much for your passions and your questions, and we were very happy to have you here today. Sebastian, do you want to say a few words as well?
Yeah, no, just thank you very much, Emmanuel. Thank you all. It's been two hours, so you have time now for coffee, for rest. But happy that to show you all these things. The software is available. Thanks to the team, thanks to Houston team, thanks to Rio team, thanks to the HQ in France for preparing this event. Thanks to Yolanda Ruiz from YPF Argentina. Thanks to Robin Domici for his great project, also from the Bureau of Economic Geology in Austin. So it's been a pleasure to present you all these things. Next version is coming soon, 6 months time. More things on SpecD, matching pursuit, we will see. We're going to try to extract more bodies, hopefully solve features from new GOM projects. And then to the UI, you'll see many things coming up within just 6 months time, so it's been short. Remarks, suggestions, feel free to interact with the teams. We try to be as responsive as we used to be. That's one of the culture of Eei, the DNA that we have is be close to our clients, be close to you. So thank you all, and of course enjoy PaleoScan. Download it right now if you wish, or just take a break and have a beer, have a coffee, whatever time it is for you. But it's been a pleasure to spend these 2 hours with you. So thank you very much, and hope to see you in real very soon. Bye.
Thank you very much, and have a great day forward, a great evening forward. Bye, everybody.
Yeah, goodbye.